What specific problem does the proposed LLM Inference-Time Self-Improvement ITSI method aim to solve, and why is this problem significant in the context of LLM advancements?
The proposed LLM Inference-Time Self-Improvement ITSI method aims to solve the problem of enhancing the performance and efficiency of large language models, LLMs, during inference without requiring additional training or parameter updates. This is significant because it allows smaller models to potentially replace larger ones by leveraging increased inference computation, thus addressing the challenges of model size and resource consumption. The ITSI method focuses on refining the decoding process through specialized algorithms that adjust logits and probability distributions, which can lead to improved task performance. Furthermore, it opens up new avenues for self-improvement with minimal human supervision, pushing the boundaries of AI capabilities beyond merely scaling model size and training data. This approach is particularly relevant as the demand for efficient and effective LLMs continues to grow in various applications.
How does the proposed method or algorithm work? Illustrate step by step the process of LLM ITSI and the distinct categories it introduces.
The proposed method of LLM Inference-Time Self-Improvement, ITSI, operates by utilizing the model's own frozen parameters to enhance performance and efficiency during inference without additional training. The process begins with the classification of self-improvement methods into three distinct categories: independent self-improvement, which modifies the decoding process using the model's existing parameters; context-aware self-improvement, which employs specialized prompts or retrieval techniques to enhance performance; and model-aided self-improvement, which integrates external models to guide the decoding process. In independent self-improvement, techniques such as constrained decoding and sampling multiple candidate generations are employed to refine output. Context-aware self-improvement leverages crafted prompts like chain-of-thought prompting to facilitate reasoning, while retrieval-based methods enhance the model's context. Lastly, model-aided self-improvement utilizes external models, such as expert or anti-expert models, to adjust logits or provide additional guidance during decoding. Each category contributes uniquely to improving the model's output quality, efficiency, and adaptability in various tasks.
Can you provide a concrete example that demonstrates the inner workings of one of the self-improvement methods discussed, such as how the controlled DAG algorithm applies lexical, vocabulary, and length constraints during generation?
The controlled DAG algorithm exemplifies a self-improvement method by implementing constrained decoding to guide the generation process. It applies three types of constraints: lexical constraints, which ensure that specific entities appear in the output; vocabulary constraints, which eliminate out-of-vocabulary words; and length constraints, which regulate the target length of the generated output. This is achieved through a Viterbi decoding algorithm that systematically evaluates possible sequences to ensure compliance with these constraints. By enforcing these rules, controlled DAG enhances the quality and relevance of the generated text while maintaining fluency. This method illustrates how structured constraints can be effectively integrated into the decoding process to improve the performance of large language models.
What theoretical or practical benefits does the ITSI method offer compared to traditional LLM approaches? Can you quantify any improvements in performance, efficiency, or applicability?
The Inference-Time Self-Improvement ITSI method offers several theoretical and practical benefits over traditional LLM approaches. Firstly, ITSI allows for performance enhancements using the model's own frozen parameters without requiring additional training, which can lead to significant efficiency gains during inference. For instance, methods like independent self-improvement can modify the decoding process to improve performance while reducing the need for extensive computational resources. Additionally, ITSI methods can enhance reasoning capabilities and increase generation speed through parallel decoding techniques, as highlighted in the paper. While specific quantifiable improvements in performance metrics are not detailed, the emphasis on efficiency and the ability to adapt to various tasks without retraining suggests a substantial increase in applicability across different domains, potentially lowering costs and improving access to LLM technologies.
How is the effectiveness of the ITSI methods validated? Describe the experimental design, datasets used, and the performance metrics that demonstrate the validity of these methods.
The effectiveness of inference-time self-improvement (ITSI) methods is validated through a comprehensive review of existing literature, primarily focusing on high-quality papers from top conferences such as ACL, EMNLP, and NeurIPS. The experimental design typically involves comparing the performance of various ITSI methods against baseline models across multiple tasks, utilizing diverse datasets relevant to those tasks. Performance metrics include improvements in reasoning capabilities, generation quality, and efficiency, often assessed through metrics like fluency, coherence, and adherence to constraints. Additionally, the paper highlights the importance of evaluating the trade-offs between inference costs and generation quality, ensuring that the methods not only enhance performance but also maintain the integrity of the generated outputs. Overall, the validation process emphasizes both quantitative and qualitative assessments to demonstrate the robustness of ITSI methods.
What limitations or challenges are associated with implementing the ITSI methods? How do these limitations affect their generalizability and practical applicability in real-world scenarios?
The implementation of inference-time self-improvement (ITSI) methods faces several limitations and challenges. Firstly, methods that depend on external data stores or models require ongoing maintenance to remain effective, while independent methods do not, which can complicate their deployment. Additionally, the amount of model access can restrict the applicability of certain methods, as some APIs provide only partial probability distributions, making them unsuitable for techniques that require full access. There are also trade-offs in inference costs. Methods that scale up inference time, such as those involving multiple generations, can lead to increased latency, which may not be acceptable in time-sensitive applications. Furthermore, the generalizability of external models is limited, as they are often specialized for specific tasks, necessitating new models or fine-tuning for different contexts, which can hinder their practical use in diverse real-world scenarios.